today I'll be presenting on time series analysis. So in the first seminar I had given an introduction about it. So in today's seminar I'll be carrying forward from where we left off and going a bit more detail into the different types of processes. So before we begin, let's just first go back a step and understand what exactly is a time series. Okay, so as the name suggests, this is a process which changes its values and it records those values as the time varies. Okay, so it records the values of a particular process at different intervals of time, and based on these outputs that we get at different times, we analyze the data and then we arrive at different estimates, and then we make predictions based on these estimates. So in time series analysis, the data that we have has different properties. So I'll just give a graph of an example. Suppose we have a milkman. So he wants to record how many liters of milk he is able to sell every day. So that he can make predictions as to how much milk he should buy from the farm and come on the next day. So suppose on one day he could sell, let's say, 20 liters. Then the next day it increased to 25, then 30. Then it remained constant, and then after some time it again increased to, let's say, 40 liters. So, and then it again increased, and then it dropped. The consumption of milk dropped, maybe due to different possible reasons, and then it again starts increasing. Then people, after people stop drinking milk, they realize, oh no, milk is actually good for us, so let's start drinking some more milk. So then they again start drinking milk, and so this increases, and it again reaches a peak when everyone starts drinking milk, and then you realize people are lactose intolerant, so the consumption again decreases. Okay, so as you can see, there are these trends observed. Okay, that there's an increasing pattern first, and then after it increases, it reaches a peak, and then it again falls, and then after this fall, there's again a rise in milk. Okay, so this is called a trend in our data, and if this happens over a period of time, over certain intervals of time, this is called cyclic. It's a cyclic pattern. Okay, first it goes up, down, and again it goes up, and again it goes down. So based on this, we can maybe for the next, like this is the first month, this is the second month. So the third month, the milkman will know that, okay, in the beginning of the month I need to get this much milk, and towards the end of the month again, he'll preferably get lesser milk. So it's more profits for him. So if you simply just analyze this data, you can actually make some very good predictions. So let's further understand how we can do this. Okay, so primarily time series can be, we can classify them into 4 types. Okay, so I'll write it here. The first type is called an AR process, auto-regressive process, and it takes only one parameter, which is P. Okay. Then the second type is called an MA process, which is a moving average process, and this also takes just one parameter, which is Q, denoted by Q. The third type is called an ARMA process. Okay, so it involves both the first and the second type, and it takes 2 parameters, which is P and Q. And the fourth type, okay, so now that we've combined both and we will use up the third one, let's go for one more step ahead, and it's called an ARIMA process. Okay, so this includes a third parameter. Okay, so it's PDQ. So let's just go a little deeper into this and understand the mathematics behind this. Okay, since we're all math students, let's just understand what is actually going on. It's easy to see the data and see what's happening, but once you actually understand, it'll make more sense to you. Okay. So the first process, like I said, is called an auto-regressive process with one parameter P. So I'll just write the general mathematical form of this. So this takes the form xt So now let's understand what all these symbols and all mean. So xt denotes the value the process takes at time t. So this is what we need to find, okay? So if we know XP is basically, suppose on the first day, he gets 20 liters of milk. So you need to put in different parameters, so the process will say, okay, get 20 liters. So XT is nothing but the value the process takes at time t. Okay. Then mu is a constant term, it's added in the equation, like how suppose there's a graph. So we have a slope and an intercept. So you can think of this like an intercept. Then alpha 1 is like a weight. In a way, it's the alpha is the parameter that quantifies the relationship between the past value and the current value. So you can think of it like how you add weights, where xt minus 1 is the value the process took yesterday. Xt minus 2 is the value it took 2 days ago. So if suppose alpha 1 is high, you give it a high value of like 0.9. Okay, suppose I give this 0.9 and I give this 0.7. So you can think of these alpha as different weights. Okay, I want to give more importance to this because the value yesterday has more impact on my value today. It is definitely more than it had, like the value 2 days ago had. So these alpha are nothing but weights. And alpha p is basically, we want to consider p is the parameter, like I had said over there, that ARP. So p is the number of parameters we want to involve in our model. So ideally p should be, you need to find like an optimal value. You can't go and say, okay, to find the value of tomorrow, I'll go back like 30 years. But then we face problems of, say, overfitting, how we learned in machine learning. So you need to kind of find the right balance. Okay, so to do this, to find the value of p is basically how many parameters or how many days back I want to go to find my value for tomorrow. You need to find p, and there are different ways to this. Like there's one thing called AIC, which is called Akaike's information criterion. So it's basically based on like how important the value is, and like if I go back too many parameters, then my model will not be able to take so much data. So then there's an overfitting, that if I'm adding unnecessary values which don't really have meaning, but I'm just including them for the sake of going back, so it doesn't necessarily mean my model will be more precise. Because suppose I want to know how much milk to get tomorrow from the farm, so I'll go back say 5 years. So you might think, oh, there's more data, so it's more precise, but the value 5 years ago does not have much relevance. Okay, so it's very important to find this value of p. Okay, and the last term, this ET, even though it seems like a very small thing, I would say ET is basically the most important thing in all this, because ET is actually the error. So I made a prediction of, suppose yesterday I had to get 15 liters, but I ended up only selling 10 liters. So the error is 5. So this error is only what you want to find. The second you find this error, it's all over, because at the end of the day, you're only trying to find the difference between how much you needed to get and what you thought you're going to get. Okay. So actually, our main goal in all this is to find ET. The second you find ET, it's basically that you know everything. So the process, this is an indeterministic process since there's an error term. The second it becomes deterministic, when you know the error term, that's when you know, then there's no point of doing all this, because there's nothing to predict, because you can say with certainty that, okay, this is going to happen. Okay, so now that I've just given a bit of a brief of this general equation of an AR process, let's understand some more characteristics about it. So in this equation, if I take xt minus mu on one side and I write this entire thing as it is, so now let me equate, let xt minus mu is equal to yt. Okay, I just want lesser parameters. I don't want to be dealing with so many unnecessary parameters. So this equation changes its form to yt, since xt minus mu is yt. Okay, so that means xt minus 1 minus mu. Can someone tell me what will it be? Yeah, very good. So xt minus 1 minus mu will be yt minus 1. So the equation changes to yt is equal to alpha 1 times yt minus 1 plus alpha 2 yt minus 2 plus this error term. Okay, and up to up to the values of p that we are including. Okay, so then if I write this, so I can write my error term as nothing but, okay, before we do that, suppose that I just want to include one parameter. Okay, so suppose in this I'm taking my p equals to 1. Okay, so to know how much milk I want to get tomorrow from the farm, I'm saying that value entirely depends on how much milk I took yesterday. So that's what this means. When I say p is 1, I'm confident that it only depends on how much milk I took yesterday. So this equation, ARP process, turns into an AR1 process. Okay, so that becomes a yt is equal to alpha 1 yt minus 1 because alpha p, right? So it goes alpha 1 and yt minus 1 plus et. So I can write this as et is equal to yt minus alpha 1 yt minus 1. So I can write my error terms, the error in terms of the values that I had today and yesterday, the difference in the values of yesterday and today. So it makes sense, okay, that error is a difference. So okay, now let's see what comes ahead. Okay, so that was about the first type of process, an AR process. Now let's move on to the next type. Okay, so just recap, AR process takes the values of yesterday. Now let's go on to the second type, it's called an MA process, moving averages process. The parameter used here is Q. Okay, so the MA Q process. Okay, so I'll write the general form of it, the mathematical form. This process is of the form xt is equal to mu plus beta 1 times et minus 1 plus beta 2 times et minus 2. So E over here is the error term. Okay. So in a AR process, I was taking the values I had yesterday, but here I'm taking the difference, like the error of what the mistake I made yesterday plus the error I had 2 days ago plus the error I had 3 days ago. Okay. So you don't understand the fundamental difference between what these two processes are. Okay, so if you want to think of it, you can think of it like, one way to think of it is that suppose you give an exam, a 100-mark exam, and you score 95, okay, in that. So you don't really look at, okay, I scored 5 or 5, 5, 5. You directly go to see where your mistakes are, right? That makes sense? So that's what this process does. It's not really paying much attention to what it got right, it's paying attention to what mistake it made. Okay, so you lose like 1 mark, you're like, okay, where did I lose that 1 mark? That's what you're more interested in. So that's what this process does, okay? An MAQ process. And the parameter Q, again, you need to decide it very carefully, how many error terms you want to include. So that's about this process. And yeah, so that's the fundamental difference that between the two types of processes. Then again, you can write xt minus mu. Okay, I can write it as yt, just to make it simpler and involve lesser parameters. So yt is nothing but beta 1 times et minus 1 plus 1 till beta q times et minus q plus et. Okay. So if you see one more characteristic of this type of process, okay, it's called a MA processes are stationary processes. And I'm not going to tell you what a stationary process is, but basically what a stationary process is that the expectation of the process is 0. That the value the process takes is usually tends to this constant, not 0, I'm sorry, constant. Okay, and the variance is also constant. So let's just go ahead and prove it. It's easy to do that. So if suppose I take an MA1 process. Okay, MA1 process, that means Q is equal to 1. So I'll put the total here. Okay, so yt is equal to beta 1 et minus 1 plus et. Okay, absolutely. So now I want to say that the process is constant, which means that the expectation should, the process is stationary, so the expectation will be constant. I'll just show that here. Okay, so that means my expectation of yt is nothing but expectation of this term plus expectation of this term. Is nothing but expectation of beta 1 et minus 1 plus expectation of et. Okay. And then if like I told you before, beta 1 can be thought of as weights. Okay, so beta will be a constant, so it comes out of the expectation. So this becomes beta 1 times expectation of et minus 1 plus expectation of et. And these error terms, okay, this is called a white noise term. So in stats, you can say that error terms are believed to follow a normal process. So et, the error terms, all these error terms bounded distribution with two parameters. Okay. So if I say expectation of the error term is 0, right? So this becomes 0 and is equal to beta 1 times expectation of this error term. Expectation of all error terms follows that normal process with mean 0 and variance sigma square. So beta 1 to 0. So as you can see, this is 0. Okay, so it satisfies the first condition of being stationary. Okay, now let's look at the other condition. Okay, so the other condition is that the variance should be constant. So if I talk about variance of my process, okay, it should come out to be constant. So let's prove that. So variance of anything can be written as the covariance, like suppose variance of A can be written as covariance of A comma A. Basically the covariance of that term with itself is nothing but the variance. So this is covariance of yt comma yt. Okay. So if you all remember, I have written it as yt is nothing but for a MA1 process with just one parameter, basically with q is equal to 1. This is nothing but yt yt minus beta 1 times of et minus 1. Okay, yeah, comma yt minus beta 1 times et minus 1. Okay. Yeah. Okay, so now if I take these, like how covariance can be separated. So I'll take this as covariance of yt with yt and minus the covariance of this yt with this term. Okay, so if I write, I'll have to expand and write it. So let me do that. So yt comma yt minus, and beta is a constant. Okay, so I'll just write it outside the covariance term. Beta 1 times covariance of yt with et minus 1 minus beta 1 times, so again minus beta 1 times covariance of et minus 1 with yt. So this is the same as this. Covariance of a comma b is the same as covariance of b comma a. And so minus the covariance of this term with this. Okay, so if I take this, so minus into minus will become plus, beta 1 into beta 1 is beta 1 square. So this is nothing but plus beta 1 square times of covariance et minus 1 comma et minus 1. Okay. So covariance of yt comma yt can be written as variance of. Okay, 1 second.
Start with covariance.
Yeah, no. So I actually made a mistake here. So instead of for yt comma yt, I didn't have to include this yt. Yeah, so this will just 1 second. Yeah, so yt already here. So yt is nothing but beta 1 times et minus 1 plus et. Okay, so this is what yt is. So that's what it is. So beta 1 times et minus 1 plus et, comma beta 1 times et minus 1 plus et. You don't understand this? Instead of yt, I wrote this. So previously I written yt again. That was a mistake. Okay, so we'll just make a few changes. So this becomes covariance of beta 1 times et minus 1 with beta 1 times et minus 1. Okay. So that is nothing but beta 1 square times covariance of et minus 1 comma et minus 1. And then if I take, so I took this and this, now I take this and this. So this becomes plus beta 1 times covariance of et minus 1 comma et. Okay. And the next term will become covariance of beta 1. So I have done this and this, this and this. So now I'm left with this and this and this and this. Okay. So this, the next term will be covariance of et comma et minus 1. So plus beta 1 times covariance of et comma et minus 1. And the last term will be nothing but covariance of these two terms. Okay, so covariance of et comma et. Covariance of okay. Yeah, so now this looks better. Alright. as we know, I told you that these white noise processes follow a normal distribution with mean 0 and variance sigma square. Okay, so the covariance of this is covariance of et minus 1 comma et minus 1 is nothing but variance of et minus 1, and the variance is nothing but sigma square. So this becomes beta 1 square times sigma square. And now covariance of et minus 1 comma et. So an assumption in time series is that error terms are independent of each other. They follow they are IIDs, independent and identically distributed random variables. Okay, so that means that et minus 1 and et are independent. That means they have the covariance will be 0 between them. So then this becomes plus beta 1 into 0. Okay, plus again. That means what this is trying to say is that the error made yesterday and the error made suppose 2 days ago are independent. They don't have any relation. That's an assumption here. So again, this term will also become 0. Plus now that term becomes variance of et, which is sigma square. Okay, sigma square. So this basically removing the 0 part, what we are left with is sigma square into 1 plus beta 1 square. Okay, so the variance comes out to be sigma square into 1 plus beta square. So if you all just take a look, what are we studying? Time series, and there's no time term in this. What that's trying to say is that this variance is constant. All the time terms have vanished. Okay, so that's why MA process is called a stationary process, because the value of its variance does not depend on time. Okay. Yeah, now let's just take a look at a few graphs so you'll get a better, you can visualize what I've been talking since so long. Yeah. Okay, so I had spoken about milk, right? Selling milk. So you can think of that as the sales data. So if I plot it, you can see the graph here that there's a bit of a pattern. You can notice it increases, then it decreases, then it's going up, down. Okay, and then at the end of 2014, it has highly gone up. So maybe the cows have increased in the country or something because of which the milk increased. So these are all how do you say it? It's just you need to try you see the data and then you try to think of what could have caused this. So you can make decisions in the future based on okay, now maybe in 2014 this happened, so maybe 2024 this can happen. Okay. So all this, you look like it's easy to say all this in retrospect. I can stand here and say 10 years ago this happened because this was the reason, but it's very tough to make predictions. And if you can make predictions easily, then like I said, that error term is the main thing what we are trying to find. If you find that, then there's no point of all this. Okay, so now this is the next data. If I talk, it's like a water data, the water in the reservoirs in suppose a village. So I converted into a time series object. So this is representing how much water was there in each month of 2010 up to 2014. Again. So the first model, this model is plotting the values. Okay, that this is how much sales are made. But now this data of water, okay, so this is again the values. So you can see a more of a seasonal pattern here. Okay, it's going up, down like that. And now I'll difference it. Okay, I'll take a difference of the data. This D is taking the difference, that the value today and the value yesterday. And now I'll plot this difference. So if you see the difference, I had spoken about this in the previous seminar, that the difference is more important because I want to know why there's such a big difference in 2013 to 2014. So it's very high. That means, again, now there must be some global warming or something because of which this happened. So that's what we're trying to find. We are more focused on the difference and why there was such a drastic change. As long as there's less change and things are moving the way they are, it's fine. But what is the reason for such a big change? Okay, so that's what we try to find. And that's what this MA model does. It takes the error term. So this difference can be thought of as the error term. So that's the difference between an AR model and an MA model. That this is going to plot the difference in the data, which is more important. And yeah, okay, so you can see that the diagram suggests, like, even by plotting like a basic, just plotting the values and plot of those, you can say so much about it. So then if you use more parameters and little more advanced models, there's lots more you can do with this. Okay, now let's go on to the third model, which is an, okay, so like I told you before, it's going to be combining both So arma PQ, right? So this should be like best of both worlds, including both. Okay, so again, now this is an arma model involving both. Okay, so I'm having two parameters P and Q. So if I write the general mathematical form, I'll write it fast. So xt is equal to mu plus alpha 1 times xt minus 1 minus mu plus I go all the way till p parameters alpha p times of xt minus p minus mu plus. So this is the AR part. Now let's see the MA part. That had Q, right? If I remember, and error terms. So this will be beta 1 times et minus 1 plus beta 2 up to beta q times of et minus q plus et. Okay, so this error term finally. So now again, like I've done it in the previous ones, so let xt minus mu is equal to yt. Okay. So this becomes, this entire thing changes to yt is equal to alpha 1 times yt minus 1 plus alpha p times yt minus p plus beta 1 times et minus 1 plus beta q times et minus q plus et. Okay. And now if I take all these terms to the left hand side, so it becomes yt minus alpha 1 times yt minus 1 minus this up to alpha p times yt minus p. Okay. So if I take this, so yt minus alpha 1 times yt minus 1 up to minus alpha p times of yt minus p is equal to, and this as it is. So now I take yt constant. Okay. So this becomes 1 minus alpha 1 times of, I'll write this symbol b. Okay, so you might be wondering what b is. So b is nothing but a backward shift operator. Okay, backward shift. So what it does is, if I apply b to any function, say xt, it shifts the value back by one time period. Okay, so b of xt is nothing but xt minus 1. Okay, so I can represent yt minus 1 as nothing but backward shift operator applied on yt once, and I can write yt minus 2 as backward shift operator applied on yt twice. Okay, so this becomes yt into 1 minus alpha 1 times beta minus alpha 2 times of beta, not beta, b square up to minus alpha p times of b raised to p. Okay, b raised to p times is nothing but yt minus p is equal to. So now from here I'll take et constant. Okay, this et constant. So this becomes 1 plus beta 1. So beta 1 times b. Okay, so this b will nothing be multiplied with et to give you et minus 1. Okay, so you are getting the same term. And you add this up to beta q times b raised to q. Okay. So if I combine all this and I combine all this, so I can write this entire process as yt, I can write it as yt times phi of b is equal to nothing but et times theta of b. Okay, so this phi of b is called the characteristic equation of an ER process, and this is called the characteristic equation of an MA process. So this is actually used to find the stationarity and invertibility of these two processes. So we can go a little deeper to that some other time. So basically you can see that this ARMA process is involving both the first type and the second type. Okay, so that's how you get the general equation of this. And so this is about the ARMA process. Now let's just see one last thing, which is about how to make predictions using these time series. So there's a technique called exponential smoothing, which is used to make predictions. Okay, so let's see how that looks like. What that looks like. And this is just one of the techniques used. There are several techniques you can use involving time series. So what this does is, it takes for the prediction, okay, this gives a one-step prediction that if I'm sitting today, I want to predict the value of tomorrow. So it only gives you a one-step prediction. So xt hat is like an estimate. So xt hat of one time period ahead, okay, is nothing but alpha times the actual value what this equation is trying to say is that the prediction made for tomorrow is nothing but alpha times the actual value of today plus 1 minus alpha times what I had predicted yesterday of today's value. Okay, so that's what this is fundamentally trying to say. And alpha can be thought of, you need to take a value between 0 to 1 and you can like change the values, and then whichever value works best for you, you should use that. So this is nothing but a one step ahead forecast, and you use exponential smoothing. Let's see that with the help of a graph once. Okay, so this is just like a random data set. Okay, same as before, like I have plotted the values of the data set, and so now we need to predict. Suppose now we are sitting at 2018 and I want to predict the value for the next month of 2018, like January. So then using these processes, you can just run the function, and how there's a predict function over here, so that predicts the value of n dot ahead, means it predicts the value of 8 time periods ahead. Okay, that's the unit. And then you add it. So this is like, okay, so this is for the entire 2 years. Okay, since our data is divided into 4 quarters, like 1 year into 4 quarters, so 8 quarters will be 2 years. So 2018 to 2020 it predicted it. So yeah, you can use exponential smoothing, and there are several other. There's one more technique called Box-Jenkins methodology. So yeah, there's lots. Actually, time series is quite a vast topic. So yeah, that's all I would cover for today. Okay, any questions? So ma'am, there's a textbook which I've referred to on time series.